Look at any busy airport in the world. Gate after gate, runway after runway, the aircraft are white. Not the same shade, not the same logo, not the same airline, but almost universally, the same base color. This is not tradition. It is not coincidence. And it is not simply because white looks clean. Every square meter of that white surface is doing several jobs simultaneously, and the story of how white became aviation's default color involves physics, economics, safety engineering, and one number that airline accountants think about every single day. The assumption that commercial aircraft have always been white is incorrect, and understanding why the industry moved toward white requires understanding where it started. In the early decades of commercial aviation, through the 1920s, 30s, and 40s, aircraft were anything but standardized in their appearance. Airlines understood from the beginning that their aircraft were moving billboards, the most visible physical expression of their brand identity, and they treated them accordingly. Bold colors, distinctive liveries, and experimental design schemes were common as carriers competed to establish visual recognition in a rapidly growing industry. Many early aircraft were not painted at all. The polished aluminum skin of a well-maintained aircraft had a brilliant, mirror-like quality that became genuinely fashionable in mid-20th century aviation. Airlines including TWA and American Airlines operated fleets of gleaming, unpainted aluminum aircraft that projected an image of technological modernity. The polished metal look required no paint, saved the weight of a paint application across thousands of square feet of fuselage, and photographed beautifully in the promotional materials of the era. The shift toward predominantly white aircraft happened gradually through the 1960s, 70s, and 80s, driven not by aesthetic preference but by a convergence of practical pressures, some related to new materials being incorporated into aircraft construction, some related to the economics of operating increasingly large fleets, and some related to hard lessons learned about heat, maintenance, and the true cost of a paint job when multiplied across hundreds of aircraft flying millions of miles per year. The most physically fundamental reason for white aircraft exteriors is thermal management, and it operates through the same basic principle that makes a black car unbearable to enter on a summer afternoon while a white car parked beside it remains comparatively tolerable. Every surface exposed to sunlight absorbs some portion of the solar energy striking it and reflects the rest. The ratio of absorption to reflection depends on the color and surface properties of the material. Dark colors absorb a high proportion of incoming solar radiation and convert it to heat within the material. White surfaces reflect the majority of incoming solar radiation, absorbing relatively little and therefore heating relatively slowly. A commercial aircraft sitting on a tarmac in direct sunlight is exposed to solar radiation across an enormous surface area. A Boeing 777, for example, has a fuselage surface area of approximately 1,000 square meters. In direct midday sun at a warm climate airport, think Phoenix, Dubai, Singapore, the solar energy striking that surface is substantial. A dark-colored aircraft absorbs much of that energy and transfers it as heat into the fuselage structure and ultimately into the cabin interior. A white aircraft reflects most of it. The practical consequences are significant. Heat absorbed by the fuselage must be removed by the aircraft's air conditioning and pressurization systems to maintain a comfortable and safe cabin temperature. These systems are powered by bleed air drawn from the engines, and drawing more bleed air means burning more fuel. An aircraft that runs its air conditioning harder because its dark exterior is absorbing more solar heat is burning more fuel on every flight, at every warm weather airport, throughout its entire service life. Additionally, excessive heat cycling, repeated heating and cooling as an aircraft goes from a sun-baked tarmac to the minus 55 degrees Celsius environment at cruise altitude, creates thermal stress in the aircraft's structure and materials. Every material expands when heated and contracts when cooled. Repeated cycles of large magnitude thermal expansion and contraction fatigue materials and accelerate wear on seals, fasteners, and structural joints. A white exterior that absorbs less solar heat during ground operations reduces the magnitude of these thermal cycles and extends the service life of the aircraft's components. Beyond thermal management, white provides a safety advantage that aviation maintenance engineers consider genuinely important. It makes damage visible. Commercial aircraft undergo constant physical stress throughout their operating lives. Pressurization cycles, the repeated inflation and deflation of the fuselage as the aircraft climbs to altitude and descends, impose structural loads on the airframe with every single flight. A typical commercial aircraft completes thousands of pressurization cycles over its service life, and the cumulative effect of these cycles can produce fatigue cracking in the aluminum skin, particularly around windows, doors, and other structural discontinuities. Identifying these cracks early, before they propagate to a length where they become structurally significant, is a fundamental requirement of aircraft maintenance. The earlier a crack is found, the simpler and less expensive the repair. A crack found late, after it has grown through multiple inspection cycles, may require far more extensive structural work and longer aircraft downtime. A white surface makes these inspection tasks substantially easier. Cracks in the paint, corrosion developing beneath the surface, oil or hydraulic fluid seeping from joints or fittings, bird strike damage, ground equipment impacts. All of these anomalies appear as clear visual contrasts against the white background. A dark or brightly colored surface can mask these indicators, making them harder to spot during the quick visual surveys that form the first line of aircraft maintenance inspection. This is not a hypothetical concern. Aviation maintenance professionals consistently report that white aircraft are easier to inspect thoroughly in less time, a meaningful operational advantage when an aircraft needs to complete its inspection within a tight turnaround window at a busy airport. The economic arguments for white aircraft exteriors operate on several levels simultaneously, and their cumulative effect on airline profitability is substantial enough to drive fleet-wide decisions at the highest levels of airline management. Begin with weight. Paint applied to a commercial aircraft fuselage is not a negligible quantity. A full paint job on a large wide-body aircraft like an Airbus A380 or Boeing 747 uses approximately 500 to 600 kilograms of paint, roughly the weight of 4 or 5 passengers with their luggage. This weight is carried on every single flight the aircraft makes, contributing to the fuel load required to maintain altitude and speed. Over the course of a year, an aircraft completing hundreds of flights burns a measurable quantity of additional fuel simply to carry the weight of its paint. White paint applied in a single uniform layer is the minimum viable paint application for a commercial aircraft. More elaborate color schemes, darker base colors requiring additional primer layers, complex gradient designs requiring multiple color applications, full livery designs covering the entire fuselage in non-white colors add paint mass beyond this minimum. The additional weight, multiplied across every flight over the aircraft's 20 to 30-year service life, represents a real and calculable fuel cost. Airlines that have done these calculations have consistently found that darker or more elaborate paint schemes cost measurably more to operate than white ones. Beyond weight, white paint offers a cost advantage in maintenance and repainting cycles. White paint fades less noticeably than darker colors under the combined assault of ultraviolet radiation, temperature cycling, and the mechanical abrasion of high-speed flight through air, rain, and occasional ice crystals. Fading on a white aircraft is barely perceptible until it becomes quite significant. Fading on a dark blue or red aircraft is visually obvious long before it reaches the same objective degree of degradation. Airlines operating dark-colored fleets must repaint more frequently to maintain the consistent brand appearance their marketing departments require. Repainting a commercial aircraft costs between $150,000 and $300,000 and takes the aircraft out of service for 1 to 2 weeks. The frequency with which this must occur is directly influenced by the color chosen. Perhaps the most significant economic factor is flexibility in the aircraft leasing market. Modern airlines do not own their entire fleets outright. A substantial proportion of commercial aircraft worldwide are operated under lease arrangements. The airline pays to use the aircraft for a defined period, after which the aircraft returns to the lessor and is placed with a new operator. Global aircraft lessors maintain fleets of hundreds or thousands of aircraft, transitioning them between operators continuously throughout the aircraft's service life. A white aircraft moving between lessees requires only the removal of the departing airline's logo and livery elements, decals and accent stripes, and the application of the new operator's markings. The base white coat remains. A full-color aircraft requires a complete repaint to transition between operators, a process that costs more, takes longer, and keeps a revenue-generating asset out of service for an extended period. For lessors managing large fleets with continuous aircraft transitions, this difference in transition cost and time is commercially significant enough to make white the strongly preferred base color for leased assets. There is one additional argument for white aircraft that operates in the most serious possible circumstances: emergency location and rescue. When an aircraft makes an emergency landing, on water, in a remote forest, in mountainous terrain, the speed with which search and rescue teams can locate the aircraft and reach survivors is directly influenced by how visible the aircraft is from the air and from a distance. White aircraft are significantly easier to spot against most natural backgrounds than dark-colored aircraft. Against ocean water, against forest canopy, against most terrain types, white provides high contrast and reflects light in ways that make it detectable from greater distances, under lower light conditions, and in more adverse weather than darker colors would. This factor is not the primary driver of the industry's color choice. The economic and thermal arguments are more consistently compelling in day-to-day operations. But it is a genuine consideration in aircraft design philosophy, and it represents one more situation in which white proves to be the more functional choice. The branding compromise that most airlines have arrived at, white fuselage with colored tail, logo, and accent stripe elements, preserves all the practical advantages of white while still allowing meaningful visual brand differentiation. The tail, which is the most visually prominent surface of an aircraft viewed from the gate or from a distance, provides ample space for bold color and distinctive design. The fuselage, which comprises the vast majority of the aircraft's surface area, remains white and continues delivering its thermal, maintenance, weight, and economic benefits. A color choice that appears to be the result of convention or conservatism turns out, on examination, to be the result of converging pressures from physics, materials science, economics, maintenance engineering, and emergency response planning, all pointing independently toward the same answer. White reflects heat, reducing thermal stress and air conditioning load. White reveals damage, making maintenance inspections faster and more reliable. White minimizes paint mass, reducing the fuel cost of carrying that mass across a lifetime of flights. White fades invisibly, reducing repainting frequency and the cost associated with it. White transitions efficiently between operators, maximizing the commercial flexibility of leased assets. And white is visible in emergencies, when visibility genuinely matters in ways that have nothing to do with branding. No single one of these arguments would be sufficient to determine a global industry standard. Together, they are overwhelming. The aircraft is white because every serious analysis of the alternative leads back to the same conclusion. The next time you look up at a white aircraft tracing a contrail across a blue sky, or watch one taxi past a terminal window, you are looking at the answer to an engineering equation that took decades of operational experience to fully solve. The color is the solution. And the question, it turns out, was never really about aesthetics at all.